You step outside and immediately feel it. The air drops in temperature, and a sharp gust of wind shakes the leaves above you. Looking at this cross-section of the Earth, that incoming storm is happening right here, in the troposphere. This is the lowest layer of our atmosphere, a blanket of air sitting directly on the surface where all weather takes place. Animals and humans are naturally wired to detect these atmospheric shifts. Frogs begin croaking in anticipation of rain, and human skin reacts to falling temperatures. But these biological alarms are limited. Feeling a chill in the air right now does not tell you if that storm will drop 2 inches of rain by tomorrow morning, or if a severe pressure system is going to hit your exact location 3 days from now. To predict what happens next, scientists move beyond these physical sensations and begin recording the specific variables of the troposphere. The process begins by breaking down the physical experience of weather into isolated variables. The first two are the physical heat we feel on our skin, temperature, and water falling from the sky, which is precipitation. This diagram represents a third variable, atmospheric pressure. It is the weight of the sky. A dense column of air molecules presses directly down onto the Earth's surface at sea level. As we move to a high mountain peak, the air column is much shorter, leaving fewer scattered oxygen molecules available to breathe. That decrease in pressure is the reason climbers experience breathlessness at high altitudes. These varying pressure levels create our fourth variable, wind. When a high-pressure zone packed with air sits next to a low-pressure zone, the air naturally moves over to fill the gap and find balance. That movement is wind. Finally, there is humidity. If the air is already crowded with moisture, the sweat on your skin cannot evaporate efficiently. This is why a humid coastal city leaves you feeling sticky compared to a dry desert at the exact same temperature. To track these distinct forces, meteorologists use a specialized toolkit. They rely on mechanical instruments to assign numbers to what is otherwise invisible. This instrument is an aneroid barometer. It records the physical weight of the atmosphere using a small, flexible metal box inside. As the outside air pressure changes, the box expands or contracts, moving levers to output a precise reading. Here is a rain gauge. By utilizing a simple funnel at the top, it collects falling water and channels it down into a numbered measuring cylinder to capture exact precipitation volumes. Measuring wind requires splitting it into 2 separate data points. This anemometer uses a 3-cup mechanism that catches the moving air. By counting how many times those cups rotate in a specific time frame, meteorologists calculate the exact speed of the wind. By isolating these saptors and applying mechanical measurement, meteorologists convert the activity overhead into a set of readable figures. Gathering the data is only the first step. The scientific method relies heavily on error correction, because misinterpreting what these tools output leads to flawed weather predictions. Look at this wind vane. Notice how the pivoting arrow rotates across the stationary compass arms. It identifies the origin point of the wind, showing that measuring wind direction is a different process than measuring wind speed. This hygrometer displays humidity as a percentage of trapped invisible water vapor in the air. The atmosphere can hold at 80% relative humidity and still not produce liquid rain. Another frequent error is using the terms weather and climate interchangeably. Weather describes the temporary state of the atmosphere outside your window today. Climate is the long-term pattern of that same area, measured over decades. Clarifying these distinctions ensures we are interpreting our observations correctly, allowing the data to be used in practical scenarios. Acting on accurate meteorological data is necessary for the daily operations of global industries. This large windsock at the edge of an airport runway gives pilots visual evidence of the immediate wind direction. Commercial aviation relies on this data because safely lifting an aircraft into the sky requires executing takeoffs directly against the wind. The stakes are high in agriculture. Farmers plan crop cycles around temperature and rainfall forecasts. Planting seeds right before a sudden freeze can destroy a community's food supply. And the data scales down. Inside museum display cases, hidden hygrometers monitor humidity. If the air inside becomes too dry, ancient wood and canvas artifacts can physically crack. You don't need a multi-million-dollar facility to start this process. You can move from simply noticing the weather to actually tracking it yourself. By cutting the top off a plastic water bottle, inverting it as a funnel, and taping a ruler to the side, you can build a functional rain gauge to track precipitation in your own backyard. The space above us is not an empty void. It is a highly active, measurable ocean of air. By tracking its variables, we can begin to see its patterns and better navigate the world around us.